let's consider a motion parameterized by x of t equals 3 cosine of omega t, y of t equals 5 sine of omega t. We know from previous examples that this is an ellipse with semi-major axis 3, semi-minor axis 5, sketched as so. I'm not going to go through the explanation of the sketch here. We've done that. I asked the question, is this a possible path of an orbit with the sun at the center? Now, we haven't specified the units of the 3 or the 5, and we haven't specified the units of omega or t. So it's entirely possible that this might be the path of an orbit with the sun at the center. Omega is the angular frequency. It tells us through how many radians, for example, the argument of the cosine and the sine function will change per unit of time. And we know that the period of the motion, this motion occurs with a period of 2 pi over omega. This is 2 pi radians over the number of radians per unit of time. When we divide this out, we're going to end up with the number of units of time required to complete the circuit. Now let's look at our r of t and theta of t. Now what is r of t? What is theta of t for motion around this circle? So here we have a typical r of t with the accompanying angle theta that I'm not going to attempt to label. But r of t is what? R of t is the distance of a point at clock time t from the origin. So r of t is just going to be the square root of the x component squared plus the y component squared, and that's going to be squaring the x component. We end up with 9 cosine squared of omega t. The y component, 25 times the sine squared of omega t. Our angle theta is going to turn out to be, well, it's going to be the inverse tangent of the y over the x, which is 5 sine of omega t over 3 cosine of omega t, and that's going to give us 5/3 times the tangent of omega t. And unfortunately, the 5/3 can't just factor out here. We're doing the inverse tangent of 5/3 of a tangent, not the inverse tangent of a tangent, and that's going to present some complications.